I'm giving a more talk.
Oh, okay.
Is the mic working?
Great to have Tselil Schramm here, who's a professor of stats at Stanford and one of the leaders of the computational statistical gap movement. And she's going to upend some conventional wisdom, I think, during this talk. So.
Yeah, exactly. Okay, cool. So I'm in the unique position of knowing that none of you have read neither my title or my abstract, so I can just reveal it to you now. So the title of this talk is Some Easy Optimization Problems Have the Overlap Gap Property. Okay, and this is based on joint work with Schramm Li, who is a Stein Fellow at Stanford right now. And yeah, as is, I guess, the thing that has happened in almost every talk so far that I've been to, I will have to explain at first what my title even means. So the overlap gap property, but let me give you the TLDR first. So the overlap gap property is as a property of some optimization problems. And it was inspired and then later formalized based on some ideas in statistical physics, some ideas for what makes a problem, an optimization problem, computationally intractable. Okay, so the idea is that problems that have the overlap gap property should be hard to optimize. And this intuition was later formalized to give unconditional lower bounds against some restricted classes of algorithms. So like effectively just algorithms which are smooth or Lipschitz in their inputs. But then, as you can see from the title of this talk, we have shown the first non-algebraic example of a problem which is actually easy to optimize, but has the overlap gap property. And so the main message of this talk is that we should not be complacent about overlap gap property and try to understand what it is that really makes these problems hard and refine this notion. Okay, so that's the TLDR. That's like basically my abstract. So now let me tell you what is the overlap gap property. So first, let me just give you a heuristic picture of the overlap gap property. So the overlap gap property, which I'm going to abbreviate OGP throughout this talk, is basically a clustering of the near optimal solutions to an optimization problem into multiple well-separated clusters. So imagine, for example, that I have a random instance of ksat. Okay, so I have a ksat formula over n variables. So the space that I'm optimizing over is just going to be the Boolean hypercube. And my optimization is over a random objective function. Try to satisfy as many of my random ksat clauses as possible. The overlap gap property is basically when the solutions or near optimal solutions that satisfy most or all of the solution or the clauses of ksat are kind of well spaced in the hypercube. So each of these little blue blobs is a set of solutions, and you can see that they're far apart from each other in Hamming distance. Okay, there's this nice clustering structure. This is basically the overlap gap property. And yeah.
Does OGP always have to be with respect to the hypercube, or can I have it in Euclidean space? Or
you can have it in Euclidean space. Yeah, you can, there are ways to define it in Euclidean space. I'm only going to talk about the hypercube, during this talk. So, but all you need is some notion of distance between solutions, and that is all you need. Okay, yeah, by the way, like interrupt me with questions at any point in time. Thanks, Adam. So, okay, so where does this come from? So in the kind of early 2000s, late 90s, statistical physicists were really interested in random constraint satisfaction problems. And they came up with the overlap gap property as a sort of heuristic notion for what it means for an optimization problem to be hard. And if you're coming at this from the angle of statistical physics, maybe what you think of natural algorithms as doing is that like they're evolving a Markov chain over time. So imagine that I have some interacting particle system, right? And my particles are the Boolean variables of my K-stat formula. And I have some kind of Hamiltonian that's associated with the system that has to do with how many constraints of K-stat I'm satisfying. And just kind of like resampling variables one at a time according to what is going to make the value of this optimization problem good on average. You know, if you start in this cluster here, okay, it will take your algorithm, your Markov chain, a really long time to go to this cluster here, right? Because you have to unsatisfy a lot of constraints in order to move from here to here. So this is some like feeling for why this should make problems hard. But then a little bit later in the like early teens, David Gamarnik and co-authors started to show that actually from the overlap gap property, you can get unconditional lower bounds. So you can get unconditional lower bounds for Lipschitz algorithms. Okay, and now I'm going to actually tell you like a concrete overlap gap property. So this comes from the line of work that started with Gamarnik in Sudan. I think 2013 is the conference publication date for this paper. And then there were a number of important works on the way, but the line was sort of concluded by Alex Wine in 22 or maybe 2020. And they were studying the following problem, which was maximum independent set in a sparse random graph. So I'm looking at the maximum independent set in G and D over N. So this is just like a random graph on N vertices, and every edge is independently present with probability D over N. If I sample a graph from this model with high probability, the size of the maximum independent set, which I'm going to denote by alpha G, is going to be 2 log D over D times N, up to some lower order fluctuations. But the best polytime algorithm that we know can only get a set that is half this size. So here I'm going to have a 1 times log D over D times N. So it seems this is an information computation gap, right? Information theoretically, we know that almost certainly the size of the maximum clique is going to be this number, right? And the best polynomial time algorithm can only get a independent set of half the size. And this is a long-standing information computation gap. And so they were sort of trying to understand why that is. Gamarnik and Sudan proved that actually no local algorithm can do better than 1 log D over D. That means like, think about having a algorithm where I have something sitting on each node and doing a computation that only looks at some constant depth neighborhood, okay? And then as time went on, they were able to formalize this and get lower bounds against stronger and stronger class of algorithms. I'll just now tell you like how you would get a lower bound against Lipschitz algorithms or generally smooth algorithms. It's a very, very simple and powerful idea. Okay, so in order to do this, let me tell you what an overlap gap property would look like for maximum independent set. So actually to get a lower bound for Lipschitz algorithms, you need a slightly stronger property than what I told you here. You need what's called an ensemble OGP. So ingredient 1 is you'd have an ensemble OGP. Okay, so what you do is instead of thinking of a single graph sampled from this distribution, you're going to think of a family of graphs sampled from this distribution. So I'm going to sample a sequence of graphs G0, G1 through GT from G and T over N in such a way that GT and GT plus 1 are row correlated. Basically, what this means is that I will resample every edge independently with probability 1 minus rho going from GT to GT plus 1. And I'll make sure that G0 and GT are actually independent of each other by making this path long enough. Okay. By the way, everything that I'm saying right now is kind of a cartoon. Like actually what's going on in this work is a little bit more complicated, but you're able to get the gist of it, at least from what I'm explaining here. So, okay, so first I'm going to sample this family of graphs. And now what I'm going to prove is the following ensemble OGP property, okay? I'm going to prove that if ST is an independent set in GT, and S sub T prime is an independent set in GT prime of size a little bit bigger than what the algorithm can get. So let's say size at least 1 plus epsilon times this number, like log d over d times n. I'm just going to call this alg. Then it must be the case that ST and ST prime either overlap almost completely or are almost completely disjoint. So ST intersect ST prime divided by the square root of the sizes. So this number, this overlap of the two independent sets has to be either in the range 0 to, let's say, 0.1 or in the range 0.9 to 1. Right, so this is just saying that like the indicators for these sets are either close or far apart in Hamming distance, normalized so that like, you know, each of them has norm 1 basically. Okay, now it's just slightly more complicated than what I told you here, because instead of thinking about the independent sets in a single graph, I'm thinking about independent sets across multiple graphs. But it's in particular, this has to hold if T and T prime are the same thing. So, okay, and then furthermore, you also need that if T is equal to 0 and T prime is equal to big T, so these are these two independent copies that I had here on either side of this thing, then the overlap has to live here. Okay, so you have to have far apart independent sets if I have two independent graphs. So this is the ensemble OGP. And then the second step for getting unconditional lower bounds is the following thing. So think about, so imagine that I have an algorithm A, which is a Lipschitz algorithm. Basically what that means is that if I have two graphs which are close in, let's say, the number of edges that I have to delete to get from one to the other or add from one to the other, then the solutions that it outputs, the independent sets that have outputs, has to be close to each other. They can't differ by too much. So, okay, so now imagine that this is again the hypercube. And I'm going to run the algorithm on G0, and this is just going to output some set S0. And I'm going to output the algorithm on GT, and this is going to output a set ST. And from this ensemble OGP property, I know that the overlap of S0 and ST has to be small. So I know that ST lives somewhere over here. Okay, and then here I'm drawing the radius outside of which S0 has to live, right? And I also know that if I look at ST intersect with big ST, so this is some intermediate, any intermediate set along this path of graphs, this has to either be inside this little ball around ST, right? So every one of these guys has to live either here or here. Those are really my only two options, right? Because that's what this is saying. Like I'm just specializing to the case where little t is some step along this manipulation path, and big T is just this T prime. So I can either be close, almost completely overlapping, or I can be far. And now I just imagine running my algorithm on S1, right? So, okay, maybe if I run on S1, it produces for me something that's close to S0. Right, and I run it again on S2, and it's going to, or on G2, and it will produce something here, etc. But the point is that I know that the algorithm eventually has to get to here, okay? And in order to do so, at some point, it's going to have to jump across this moat, and that's not allowed for a Lipschitz algorithm, right? Like I'm always going to have that the graphs are close by because correlated random graphs are close by, and so I can't have the algorithm ever jump off this moat. Therefore, it has to fail. That's the type of argument that is done. Okay, so hopefully that.
Where does Schramm come in?
Oh yeah, so so like I didn't parameterize, like say that A is an L Lipschitz algorithm, right? And the distance between GT and t plus 1 is going to be at most rho. So, or sorry, maybe, yeah, I think that 1 minus rho maybe. So then like the distance that A is allowed to map the outputs should be, sorry, here's A, should be at most L times 1 minus rho. And so now, like, you know, this is L times 1 minus rho should be less than this gap, basically. Yeah, thanks, Evan.
I have a question. So this set of graphs G naught to GT, this property you define, is it an assumption about the graphs, or is it true that all of the graphs which are correlated will have that property?
Okay. So this ensemble OGP, as I've said, this is just a property of graphs. Like, but what I would have to do is I would have to prove that this holds with high probability.
Okay,
so like here,
there actually exists a process that will satisfy this property.
Not only does there exist a process, it's like a very simple process. Like I just sample G0 and G capital T independently from this distribution. And then one thing I can do is I can just flip one edge at a time going from G0 to GT, and that will satisfy this property.
So if I understand it correctly, I mean, here she's talking about how, okay, the Gumarnik Sudan proved a lower bound against local algorithms. And then by proving a stronger property, which is ensemble OGP, which is sort of the natural correlation for how to go from G0 to GT, then that as an abstraction implies a lower bound against a richer family of algorithms.
Exactly. Yeah, exactly. Thanks, Ankur. Okay, other questions? Okay, cool. Okay, so now, okay, so we have this unconditional lower bound for Lipschitz algorithm. So now a question that you might ask is, okay, what algorithms are actually Lipschitz, right? So, okay, so Lipschitz algorithms. So one thing that I'll say is that you don't have to imagine an algorithm which is always Lipschitz. You can have an algorithm which is usually Lipschitz. So that's also fine. And once you expand and you can also have algorithms which are like, you know, not like where the Lipschitz constant is actually pretty bad as long as you tune your correlation the right way. I mean, here you can see that if 1 minus rho is really, really small, it's okay if L is really, really big. And so once you do that, many algorithms become Lipschitz. So if you run like gradient descent or approximate message passing for a constant number of steps, in these kinds of average case settings, right, these are often provably Lipschitz algorithms. The reason why is that, you know, your objective function is, let's say it involves some random matrix, right? And the gradient would be like a linear form of this random matrix with a vector, but the operator norm of random matrices are bounded with really high probability, so you get Lipschitzness of your gradient. That's of gradient descent. Another class of algorithms, which is not exactly Lipschitz, but close enough, is low degree polynomials. So if I have a function, which when applied to G, it outputs a polynomial. This is a degree 1 polynomial in the adjacency matrix entries. Okay, because of noise stability of low degree polynomials, you can also show that this type of function is Lipschitz. Although the quantitative guarantees on this I always was a little bit suspicious of. So like, for example, in the case of independent set, what Alex Wine's result finally proved, building on prior works by Gumarnik, Jagannath, and Wine, and others as well, is that, so here's like a theorem that is due to Alex Wine. Okay, so any degree D algorithm for finding independent sets of size at least 1 plus epsilon log d times n in these sparse random graphs must fail with probability at least 1 over n to the order d. Okay, so bounded degree polynomials can't have too high of a success probability. Okay, now one reason to get excited about a lower bound against bounded degree polynomials is that for planted problems, for planted optimization problems, it seems like there's a reasonable amount of evidence that bounded degree polynomials are capturing information computation thresholds really well, right? And so you might think, well, here we have a lower bound against bounded degree polynomials. That's a pretty good thing. You might be a little bit sketched out by this fact that this probability is so small, because really, like, you'd be happy if you had a bounded degree polynomial that was even succeeding with probability half, right? Like, that's pretty good for these, really intractable problems. But anyway, this is like definitely quite interesting and much better than nothing. And the phenomenon extends beyond just maximum independent set in random regular graphs, or not random regular graphs, random sparse graphs. So the phenomenon, it seems like the OGP is going to kick in. It's known to kick in at the info comp threshold for many, many problems. So just at the moment where algorithms fail, the OGP kicks in. This is true for, so I already said independent sets in sparse random graphs. It's also true for maximum clique. In dense random graphs, this is maybe not so surprising because, independent set and clique are almost the same thing. But it's also true, for example, for random k-sat. So this is a really striking result due to Huang and Bressler. If you look at the random k-sat problem, right? The thing that makes the problem harder is when if you're trying to find a solution that's going to satisfy all the clauses, it's the clause density. Like, the more clauses you have, the harder the problem becomes. And exactly at the density where known polynomial time algorithms fail, the overlap gap property begins. So, okay, so that's pretty amazing. And now also, this is known to hold for a bunch of spin glass problems. So this is basically like optimizing a polynomial with Gaussian coefficients over, let's say, the sphere or the cube. So taken all together, I think people, including maybe at times myself, think, wow, it's pretty cool that the OGP seems to kick in exactly at the information computation threshold for all these problems. Like, maybe we can take overlap gap property to mean not just a lower bound against Lipschitz algorithms, but maybe it's a marker that this is like the computational threshold for the problem. Okay, so, but I always felt a little bit unsettled about things like this, for example. And okay, and then Shuangping and I sat down this summer and we tried to think really hard, and we just opened the intro algorithms textbook, and we looked at the list of problems in it, and we were one by one, let's check if they have the overlap gap property. Yeah, Kevin, do you have a question?
Yes. Just trying to interpret. So
yeah,
you're saying it fails with very, very small probability, but it's polynomial probability that it fails. Right. But can I not just verify what you're trying to get? Oh, over the
randomness of the instance.
Yeah, the randomness of the instance. Yeah. Over.
Okay, so for some instances.
Right, you only get one run of the algorithm. Yeah. Okay, so now, yeah, I can just tell you our main result. It's very easy, luckily, to prove.
And by the way, so do all these OGP types of statements, like this lower bound against degree D, do they all have this problem that the lower bound and the failure probability gets really bad with D, or is it okay in things like max clean?
No, they all have this problem.
Okay.
Yeah, they all have this problem. Maybe, okay, if you have a Gaussian problem, then this could be 2 to the negative OD. But still pretty bad. So, okay, so here's our main theorem. And it's basically that shortest path in sparse-ish random graphs. So here I'm thinking Gn b log n over n, where b is bigger than 1. This is just so that I'm above the connectivity threshold in order training. So shortest FT paths in such graphs have the overlap gap property with probability at least 1 minus 1 over log n. Okay, and not only do they have the overlap gap property, they have an ensemble overlap gap property. So basically what we can show is that for any constant epsilon, with high probability over correlated graphs G and G prime sampled from this distribution, any 1 plus epsilon times opt length paths P in G and P prime in G prime have to have overlap, which is either of order epsilon or 1. Can you guys still see under here? Maybe it's a little borderline.
Got the TVs.
Yeah.
Okay, and then similarly, if I have totally independent G and G prime, then it has to be the case that I'm in this low overlap setting. And from this, we have corollaries. It's unfortunate that my theorem is so big that I can't write the corollaries there, but maybe I'll just put it here. Oh, I can switch that.
So somehow, the definition of Lipschitz, is a little subtle for some of these things. Do you think like the algorithms that are polytime for this problem, there's a different definition of Lipschitz that they satisfy?
No, they don't. Like, right, okay, yeah, good point. So, okay, so first of all, as Anker notes, shortest ST path is a polytime solvable problem. Okay. Is this a Lipschitz? Is this Lipschitz? No, it is not, because you can, basically, like if I look at the shortest, so first of all, let's think about the worst case, right? So the worst case, it's clearly not Lipschitz because I can have that here's S and here's T. They have no edge between them. And here there's a log n or like an n length path. Okay. And this is going to be found as the shortest ST path in this case because we know how to solve it. But if I add in this edge, just a single edge, right, the length of the path becomes 1. So like the traditional algorithms for this are not Lipschitz. Even in average case instances, they're not Lipschitz. Okay, yeah, corollaries. So using this ensemble OGP, we can basically prove that no Lipschitz algorithm can solve the ST path problem. Okay, after much effort, we can also prove the following thing. Okay, so here, okay, so we would have liked to have an even shorter paper and to just take Alex's infrastructure, which is basically it basically shows that low degree polynomials are Lipschitz. But it's a little bit subtle, and you can only get that low degree polynomials are Lipschitz with this kind of small probability in Alex's work. For him, it's not a big deal because his overlap gap property, his ensemble overlap gap property, holds with incredibly high probability over the instance, like exponentially good probability. But you can see that for us, our overlap gap is only holding with probability 1 minus 1 over poly log n, and that's by necessity because remember that we're in G n log n over n, and the moment that you take S and T and add an edge between them, it's over. There's no more overlap gap property. Okay, and this happens with probability at least log n over n, so we can't afford to use Alex's result. Then we work pretty hard, and we're able to show that if you have a symmetric low degree polynomial, it is even more stable than Alex and David Gamarnik and Akash's prior work showed, and we can improve things to this type of bound. So we can show that no degree D the algorithm succeeds with probability greater than 2 to the negative order D. This is the only complicated part of our paper, by the way. Like proving this is really, really easy. However, let me just draw your attention to the fact that there is a logarithmic degree polynomial which solves this problem with really high probability, actually, just beyond the threshold of what we forbid here. So here, like, note that there exists a degree, actually, log n over log n polynomial, which computes the ST path probability 1 minus, again, order 1 over log n. I'll just tell you what this polynomial is. So, okay, so one thing is that it's not so difficult to compute that in this model, the length of the shortest path concentrates really, really well around log n over log n. So you know the number, you know the length of the shortest path. And now I just want to know, does the edge ij participate in the shortest ST path? So I'm going to write down a logarithmic degree polynomial that will approximate this pretty well. So I'm going to have that Fij, or Fij of g, this is going to be my approximation for the indicator that ij is in the shortest ST path. What do? I just take the sum over all paths in the complete graph between S and T containing edge ij, okay, of length opt. Opt is some, log n over log n length. And now I just take the product over edges A, B inside this path of the indicator that the edge A, B is in the edge set of G. Okay, so this is like effectively, I'm going to check if there exists some path containing the edge ij between S and T and G. I can express this as a logarithmic degree polynomial. And I normalize this in the appropriate way, and then you can check that it's a really good approximation for the indicator that the edge ij is the shortest path. So we have like right where the effectively right where our corollary from the ensemble OGP forbids the existence of a low degree algorithm, there is one, right? Like when you just become not Lipschitz enough so that the theorem doesn't forbid you from having an algorithm, we've got one. And I think that's like it's really challenging the finality of these OGP results in these other settings, right? So like all of the unconditional lower bounds that you can prove with OGP are true, but does that mean that we should stop looking for algorithms? Perhaps not. So like some questions that maybe this brings to mind are like, why are we trying to use Lipschitz algorithms to optimize these problems in the first place? So why Lipschitz algorithms? And for that matter, why low degree algorithms? So I think it makes sense to use an algorithm that you think is going to be smooth for a problem where you think that the solution to the optimization problems themselves are smooth, right? Like if you expect that when you perturb an instance, the solution doesn't change by very much, then it's reasonable to say, okay, like it makes sense for the algorithm to be Lipschitz because I want the algorithm to be robust to noise in the same way the solution is robust to noise. But the whole point of these problems, like the reason that you can prove the overlap gap property even exists, is that the solutions are not robust to noise. So it's like weird that we're ruling out these Lipschitz algorithms when, if we think about it for a second, it doesn't seem like they should be very good at solving these problems anyway, notwithstanding the great success of Lipschitz algorithms for other problems, right? Like Lipschitz algorithms are really great for other problems, but maybe not like, maybe they shouldn't be the ones that we are thinking about for these problems. even if you think about low degree polynomials, right? So in the planted setting, it's believed to be the case, or it's hypothesized that degree log n algorithms are capturing the computational threshold. The kind of like logical argument that you could make for studying low degree polynomials in this case is similarly that like low degree algorithms are noise robust and the planted structure is robust to noise. But even still, there's like the fact that we have to work out with logarithmic degree means that, you know, a lower bound of this type where you're only ruling out success that's like really tiny as a function of d exponentially small as a function of d is not that convincing. So Adam's looking at me like I'm running out of time. Okay, so I'm basically out of time, but basically I think the TLDR is the overlap gap property. Some easy optimization problems have it, and like maybe we need to not be complacent about the type of lower bounds that we're getting from this and think about how to get them to be more robust. Okay, that's it. Thanks, guys.
I did have to give you that look because the students need to get up and put their posters.
Yeah, no worries.
But real quick question, or we can just talk to. Okay, yes,
so I think there's a paper that has a title that low degree algorithms are equivalent to statistical query algorithms.
Yeah.
So is there like any implication of your work to statistical queries?
No, because okay, so that paper, the low degree and statistical query equivalence, that's inherently in this planted setting. So it's pretty different, right? Here it's like I'm trying to optimize over a solution or over a space that has no planted structure. Whereas that was for the planted setting. So it's not that I know of is the answer.
Thanks, Logan. And we'll see. It's the poster session, and hopefully there's food there as well. So we'll see you there. All right.
Yeah. No, I was gonna say something.
Yeah.